Hey everyone, in this video I'm going to go over questions 19 through 24 of the USNCO 2025 local exam. You can follow along with both the test and the solutions document I've written in the description below. So let's begin with question 19. It's asking what the melting point of 1,4-dichlorobenzene is, and to solve this question we can use Gibbs free energy. So the equation we must know for Gibbs free energy is delta G equals delta H minus T delta S. And from here, what we notice is that it's asking the melting point. And at the melting point, delta G is going to be 0, specifically when it's undergoing fusion. So rearranging, we see that delta H equals T delta S. And we're trying to find the T here, which is going to be the melting point. So we rearrange further to get the melting point is delta H over delta S. And from here we can plug in the numbers we have. We have that the delta H is 18.2 kilojoules, which is 18.2 kilojoules per mole, and then we convert that to 18,200 joules per mole. And then we divide by our entropy of fusion, which is 55.3 joules per mole per Kelvin. And doing that computation, which is shown here, we get the value 329 K. And to convert from Kelvin to Celsius, we just subtract 273. So our answer is going to be 56 degrees Celsius. Moving on to question 20, it's asking what the enthalpy of reaction is for this reaction given here. And the main equation we must know for this is this, that the fact that the enthalpy of reaction equals the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. So in this case, we notice the products are CF4 and HF, and we have two CF4s here, and we have 4 HF here. So the enthalpy of reaction is going to end up being 2 times the enthalpy of CF4 plus 4 of the enthalpy of HF, and then we're going to subtract it by our products, C2H4. And if you notice, we didn't get a value for the enthalpy of formation of F2 here, and that's because fluorine in its standard state is F2, so there's essentially no energy that needs to be added to make it into the F2 form, since that's just what it naturally assumes. So we can ignore that in the enthalpy of formation equation here, so we just subtract the C2H4. And we're going to plug in the numbers we have from this table here. So I've done the computation here below. You can see that this is the CF4, and since we have 2 of those, we multiply by 2. This is the HF enthalpy of formation, and we have 4 of those, and then we subtract by the C2H4. So doing that calculation, we get negative 2,503.6, so our answer is going to be A. Now 21, this is like essentially a 2-second problem if you're familiar with the concepts of K. A reaction is spontaneous if your K is greater than 1, and the reason for that is because if you think about what K means, it's like essentially this, right? For a reaction that goes from A plus B to C plus D. So if the K is greater than 1, the products are going to be favored, so the reaction is going to be spontaneous. However, if you want a more formal solution of it, you can look at the equation delta G equals negative RT ln K. And from here, R and T are always going to be positive, so the sign is going to come from the negative ln K. And ln K is going to be greater than 0 if K is greater than 1, and that's just coming from the ln function. So when K is greater than 1, ln k is going to be positive, but this negative sign here is going to make the sign of delta G negative. And if you remember that since a delta G being negative means that a reaction is spontaneous, if k is greater than 1, the reaction is going to be spontaneous. So let's go back to our question here. The first reaction has k much greater than 1, and the second reaction has k much less than 1. So our answer is going to be I only, since only that has k greater than 1. Now question 22, I'm going to give you a breakdown of the problem, and then I'm going to give you 3 explanations, increasing complexity, but all of them are going to be valid, and they're going to be increasing in amount of time it would take to solve using that method as well. So to break down the problem here, we're told that solid gallium melts at this value, and it has an enthalpy of fusion of this value. Then it tells us the heat capacity of solid and liquid gallium. And then it asks us what the temperature is going to be at equilibrium when you have equal masses of solid gallium at 20 degrees Celsius and liquid gallium at 60 degrees Celsius. So to break down the problem a bit, essentially the liquid is providing the heat to the solution. As it cools down, it's releasing that heat, and the solid form of it is going to take up that heat. It's going to reach the melting point, which is established here, and then it's going to start the fusion process according to this enthalpy of fusion. And the first explanation we're going to go through is really simple. I'm not even going to write it down. It's essentially saying that the very high enthalpy of fusion here, this enthalpy of fusion is very high compared to the heat capacities of the liquid and solid form of gallium. So essentially, even though the liquid is going to provide heat, the gallium is not going to fully melt and undergo that fusion process fully. So just by eyeballing the value, sort of, considering that this is kilojoules and not regular joules, we can see that it's pretty much going to stay at the melting point. And since there's no answer choice lower than the melting point, we can be sure that it's going to be the melting point, since it might be uncertain if it's going to reach the melting point, but all the answers here are above 29.8. So above or equal to 29.8. So from here, we've already sort of got an idea in our heads that this is, the answer is going to be A. It's just going to be the melting point. But the second explanation, the second method of doing it, sort of puts that more in stone. So if you're familiar with Q equals mCt, you can write Q equals nCt for n being number of moles and C being the specific heat capacity in terms of moles instead of grams. And in this case, the energy is coming from the liquid form of gallium as it's cooling down. So the Q cool is going to equal the number of moles of liquid gallium times the heat capacity of liquid gallium, and then the delta T. And considering the fact that it's coming down from 60 degrees Celsius to the melting point, this delta T is going to be 60 minus 29.8, which is the melting point. And the C is given here, 28.5. So we're just going to write that. And we're not going to bother concerning ourselves with finding this number of moles, mainly because we can't, because it tells us equal masses, but it doesn't tell us what the mass actually is. So we're just going to do our calculations per mole. So we'll plug in 1 for n. And doing this computation, we get 860.7 joules. So essentially the cooling liquid is providing 860.7 joules of energy to the solution overall. Now, although it is true that the solid gallium actually has to reach 29.8 before it can start fusion, let's just calculate the enthalpy of fusion, or the heat to essentially melt this and get it above the melting point. And that's going to be our 5.59 kilojoules, and in joules, that's 5,590 joules to melt the solid. So you can see here there's absolutely no way the solution is going to go over the melting point, because this value is significantly higher than this value. So the total heat, and considering that the cooling liquid is the only source of heat, the only heat that's coming to this solution is not enough to actually melt the solid. So it's going to stay at the melting point. So from here, we've solidified that the answer is going to be A. And if you want to look at the third method of doing it, that's the overkill method, which is in the solutions document here. We calculate the Q cool. This is what we calculated. But you also can calculate the Q heat, because that's the amount of heat the solid needs to actually reach its melting point, and then it can start fusion. So we're left with a Q net here of this. And essentially all this is saying is that it can't melt the solid fully. In fact, it can only melt 0.1 moles of solid. And considering we were doing our calculations per mole, that's not enough. So the mixture is going to remain at the melting point, which is answer A. Okay, so that was a bit of a long problem, but I wanted to break it down a bit. But now let's move on to question 23. So question 23 is asking what the KSP of AGBR is at 298 K. So the equation that we're going to use for this is delta G of the reaction is equal to negative RT ln K. And we're asked for the K. So let's rearrange for that. We have K equals E to the power of negative delta G reaction over RT. Now from here, we're just going to do some computation to essentially find this K value. And the very first step is going to be to find our delta G reaction. So we can actually just sum up our reaction here for the dissolution of AGBR, and that reaction is here. So we're going to use delta G of the reaction equals delta G of the products, or rather the sum, minus the sum of delta G of reactants. So in this case, that's going to be the delta G of Ag plus, which is 77.1, minus 102.8, because that's the Br minus, and then we're going to minus negative 96.9. And that's going to get us a value of 71.2 kilojoules per mole. So that's our delta G RxN, and we can plug that into here. And the R and T are just going to be, the R is just the gas constant, 8.314 joules per mole per Kelvin, and the K, or the T value, is given here. That's the temperature. So I've done the computation down here. Don't worry about this exp, that just means e to the power of all this. So plugging in this, and this, we get this value for KSP, and that's going to be our answer. So the key thing to note with this problem is when you're using this reaction, you have to be careful that you're actually using the reaction for the KSP. You have to put it in the form of dissolution, since that's what KSP is used for. So question 24 is asking for a reaction under conditions where it's at equilibrium. Which of the following two statements must be true? So let's go through them statement by statement. The first statement is saying that the delta S of the reaction must be greater than 0. And to disprove this, I'm going to use some dummy numbers. So let's first use our equation for Gibbs free energy. And let's plug in some numbers to showcase why this is false. So at equilibrium, delta G is going to be 0. And I guess that's a spoiler of II. But let's say that delta H is negative 400 and T is going to be 200, while delta S is negative 2. So in this case, this is negative, so this is the opposite of what the statement is saying. And if you compute this, this is going to end up being negative 400 plus 400 equals 0. So even though delta S is negative, the reaction is still at equilibrium, so I is going to be false. And you heard me earlier say that II is true, and for most people who have studied chemistry a bit, this should be something that you intuitively recognize. That's just like a fact of a reaction under equilibrium. But if you want to see kind of like a proof here, essentially the intuitive proof is that this is necessary since neither the forward or the reverse reaction is going to be spontaneous, so the system is going to be at equilibrium. But we can actually use the delta G equation under non-standard conditions to show this. So if you assume delta G is 0, then you're going to end up getting that Q equals K. And if you know what Q is, that's the reaction quotient. If Q is equal to K, then that means the reaction is at equilibrium. So it showcases how it's necessary for delta G to be at 0 for the reaction to be at equilibrium. So the answer is going to be II only.